Hi everyone, welcome back. Last time we were talking about determinants, and I want to continue our discussion of determinants. Just a few observations first. Let's say observations. Number one, if the matrix A, so let's say A has a row of zeros, then the determinant of A is equal to 0. How do you know that? We'll expand about that particular row, and you're going to have 0 times something plus 0 times something minus 0, or I guess plus minus plus minus. But it'll be zeros times other determinants. Same thing if A has a column of zeros, then determinant of A is equal to 0. Same reason, just expand about that column and you'll have zeros times various things added together. And one more observation, the determinant of A transpose is equal to the determinant of A. Why is that? Well, when you take a determinant, when you take a transpose, all you're doing is interchanging rows and columns. So if you chose to compute the determinant of A expanding about the ith row, then by expanding about the ith column of A transpose, the exact same computations are going to take place. Right? Now, for an n by n matrix A, the computational complexity of determinant of A, meaning the amount of computations, addition, subtraction, multiplication, that you need to do in computing determinant A is approximately n factorial. So it's in the neighborhood of n factorial. And n factorial grows very, very, very quickly. So if n equals 25, meaning A is a 25 by 25 matrix, computing the determinant of A on a fast computer, I don't know exactly what fast means these days. Somewhere, and let's see, what do I have here? If a computer does 1 petaflop per second, a 25 by 25, so here, 1 petaflop per second, a fast computer, computing determinant A on a fast computer takes about 300 years. So, as matrices get big, computing a determinant takes a long, long, long time. So here's what we want to do. So if you just take a random 25 by 25 matrix, you're never going to get it done, right? It'll be dead before we're done figuring out what the determinant is. So what? Well, here's what we want to remember from your computations, from what we talked about in the last lecture also. Zeros are good. Right? Each zero in A reduces the number of computations. So if we happen to have a 25 by 25 matrix and we've got a whole bunch of zeros, and we notice, oh, there's a whole bunch of zeros in this particular row or in this particular column, and we tell our computer, hey, compute the determinant by expanding about this particular row that has lots of zeros, or this particular column that has lots of zeros, then we can reduce the number of computations a huge amount. And so this 300 years, right, will no longer be in effect. We can actually do the computation fairly quickly. So let's see, each reduces the number of computations needed. And so what are we saying here? Zeros are good, right? Good meaning it makes life easier when it comes to doing the computation. Now, if we have a matrix, right, some n by n matrix, we have a process of introducing zeros into that matrix. Right? We've already done that when we were solving linear systems. That process, Gaussian elimination. So we have a process, right? And that's Gaussian elimination. That introduces zeros into a matrix. Start off with a matrix, and what's the deal? So you say, okay, let's identify a leading one and then use that leading one to create zeros below it. So the question then, and this is what we're going to do. We're going to say, all right, let's start off with our matrix. Maybe it's a huge matrix, maybe it's not. But it doesn't have a whole lot of zeros. And we notice, oh, to compute the determinant, it's going to take lots and lots of computations. If we take that matrix, perform some row operations to it, we can introduce a whole bunch of zeros, and that will make the computation of the determinant of the resulting matrix much, much easier. The question then, what happens to the determinant when you apply row operations? So, let's say it this way. Question, how do elementary row operations affect the determinant? If we can answer that question, then this leads us to a procedure of computing the determinant much, much quicker. So now let's answer this question. How do elementary row operations affect the determinant? And well, there's 3 different row operations, so let's look at each of them individually. The first one, let's say that we get the matrix B from A by performing the row operation multiply a row, so multiply row by the constant K. Then the determinant of B is equal to K times the determinant of A. If you multiply a row by K, right, it multiplies the resulting determinant by that same factor K. Okay, so there's one of the row operations. The next one, let's say that we start off with A, we do a row interchange. We interchange 2 rows to arrive at the matrix B. So interchange 2 rows. Then the determinant of B is equal to negative determinant of A. So if you interchange 2 rows, it changes the determinant by a factor of -1. And then the last of them, so the last row operation, right? If we start off with A, let me make this a little longer. Start off with A, and we add a multiple of 1 row to another row. So add multiple of a row to another. right? That's row operation number 3. In this case, the determinant of B is equal to the determinant of A. The determinant actually doesn't change. So this suggests a procedure for computing the determinant of a matrix. And so it goes like this. So given an n by n matrix capital A, what we do is we perform elementary row operations on capital A to arrive at an upper triangular matrix B. So we're going to do elementary row operations. We don't need to get all the way into reduced row echelon form. What we need to remember is that computing the determinant of an upper triangular matrix is easy, right? All we do is have to multiply along the diagonal. So now, the determinant of A is equal to some constant, m, times the determinant of B, where m is found by, and I'll just put this in quotes, keeping track of the effect of elementary row operations. So let me, I'm sorry, I was standing in front of that when I wrote it. So we compute the determinant of B, multiply it by this correcting factor, that's going to give us the determinant of A. Computing the determinant of B is easy because it's an upper triangular matrix, so all we need to do is multiply the diagonal entries. And then this m we figure out by remembering how each one of the elementary row operations changes the actual determinant. Right? So that's what I mean by m is found by keeping track of the effect of the elementary row operations. Okay, so let's actually do an example now. In fact, I'm going to do a couple of examples. Okay, so the first one, A is going to be, we'll start with a 3 by 3 here. So 1 minus 1, 4. 1 minus 1, 4. 2, 1, 4. And 1 minus 1, 3. I mean, honestly, 3 by 3 determinants are not really that hard. Usually if I see this one, I will just compute it directly without doing row operations. But I want to actually show how this process works. So I'm going to do row operations this time. But I should, just to be honest, a 3 by 3, I'll just compute it. I can, once you get good at computing determinants, you can really almost do these in your head. But when it hits 4 by 4 or more, if I don't see zeros, I'm going to do row operations to create zeros. So let's see, I want to get this to upper triangular. And so let me see what I would need to do. Okay, so here's a leading 1. I'm going to use it to kill stuff below it. So let's see. I'm going to add -2 times this row, times the top row, to the second row. So that's going to give me a 1 minus 1, 4. 0, okay, so this was -2 times this, so -2 makes that a +2. +2, so that gives me a 3. And then -2, that's a -8, so that makes that a -4. 1 minus 1, 1 minus 1, 3. What did I do here? I added a multiple of a row to another row. That does not change the determinant. Now, it's not quite upper triangular. I still need to do some more row operations. Okay, so the next row operation, I'm going to add -1 times the first row to the second row. So we'll have 1, minus 1, 4, 0, 3, negative 4, and then, so this is going to be a 0, negative 2, what am I doing? Negative 2, no. Nope, sorry. That should be 0. And then what happens here? So I am subtracting, that should be a minus 1. Let me just make sure I did all this right. Yep, 0, 0, negative 1. Okay, so this is my matrix B. How did I get from A to B? I did 2 elementary row operations, and each of them were the type of they were the third type of row operation, the one that doesn't affect the determinant at all. I added a multiple of row 1 to row 2, then I added a multiple of row 1 to row 3. That got us to upper triangular. And so, what's the determinant of A? It is exactly the determinant of B, and look how easy it is to compute the determinant of B. Just multiply these entries, and what we get is a negative 3. So that's the idea. Do elementary row operations to introduce zeros. If you get it to upper triangular, then it's very easy. In practice, oftentimes, I'll just create enough zeros to make life easy. I don't necessarily get into upper triangular, right? Upper triangular obviously is the easiest, but it's really the whole point is to simplify the computation, and so you can do whatever you want. On an exam, you're going to get a problem that says compute the determinant on this exam that's coming up on next Friday. Let's see, when we see this lecture. Yeah, so it'll be, I think this is Friday's lecture, so a week from tomorrow. Sorry, it's confusing. Today is Thursday for me. You'll be seeing this on Friday. So anyways, it'll be roughly a week. On that exam, you're going to be asked to compute a determinant, and it'll be some messy looking matrix. You will want to do some row operations to simplify things. So let's try one more example where we use this idea of simplifying the matrix by applying elementary row operations and then computing the determinant. So here we're going to do a 4 by 4. A is the matrix, row by row 1, 2, 0, 1. And then 3 minus 1, 1, 2. Then 0, 2, 2, 1. And then the last row is a 1, 1, minus 1, minus 1. 1, 1, minus 1, minus 1. All right, so I already have a leading 1 right here. I'm going to use that leading 1 to turn each of the entries below it into zeros. So the first step, I'm going to add negative 3 times the first row to the second row. So this will give me a 0, negative 3, negative 6, negative 7, and then 1 here, and this will be negative 3 plus 2 gives me a negative 1. 0, 2, 2, 1, 1, 1, minus 1, minus 1. All right, next step, I'm going to use this leading 1 to turn that 1 at the bottom into a 0. And so this is going to go like this, 1, 2, 0, 1, 0, minus 7, 1, minus 1, 0, 2, 2, 1. And then I need to add negative 1 times the first row to the second row. So that will give me 0, negative 1, negative 1, negative 2. Good. And now, so what have we done so far? The elementary row operations have been add a multiple of one row to another row, and remember, that does not change the determinant. So the determinant of this matrix right here is exactly the same as the determinant of this matrix. Now, I see a negative 1 right here. I want that to be my leading 1. So what I'm going to do next is I'm going to interchange rows 2 and 4. So that's going to be 1, 2, 0, 1. 0, minus 1, minus 1, minus 2. 0, 2, 2, 1. And then 0, minus 7, 1, minus 1, right? So all I did was interchange rows 1 and 2. Now we're supposed to keep track of the row operations, and what just happened, because I interchanged, that multiplies by a negative 1. So what I do is I'm going to put a minus 1 and I'm going to circle it here to remind myself that when I get to this final result, the difference between the original determinants, or matrix's determinant, and the final one differs by minus 1. Okay, next step. Okay, well, I've got a negative 1 here. I actually need it to be a leading 1, so I need it to be a positive 1. So 1, 2, 0, 1. I'm going to multiply the second row by negative 1. 0, 1, 1, 2. 0, 2, 2, 1. 0, minus 7, 1, negative 1. And when you multiply a row by a constant, that changes the determinant by exactly that constant. So I multiplied here by a negative 1. Right? And I'm going to keep track of this now. All right, so now, let's see, I need to turn the entries below here into zeros. So I'm going to do negative 2 times row 2 plus row 3. 1, 2, 0, 1. 0, 1, 1, 2. 0, 0, 0. Right, because that'd be negative 2. Negative 2 times this one is a negative 4 plus this one. Wait, negative 4 plus this is negative 3. And then we have 0, minus 7, 1, negative 1. And now I wish I had a bigger board, but I'm running out of space, so I'm going to have to move back up to here. And so just remember what we've done. I'm going to have to erase this stuff, but we've multiplied by negative 1 and then again by negative 1, which means that at this point, our original matrix A has exactly the same determinant as this matrix right here. All right, so my next step, I want this to be a leading one. So I'm going to add 7 times this row to this row. So we've got 1, 2, 0, 1, 0, 1, 1, 2, 0, 0, 0, negative 3. And, okay, so this is going to be a 0, 0, so 7 times this one. Okay, 7, this will be a 7 plus 1 gives me an 8. And 7 times this is a 14 plus this is a 13. All right, we're almost there. My last step, I'm going to interchange rows 3 and 4. 1, 2, 0, 1, 0, 1, 1, 2, 0, 0, 8, 13, 0, 0, 0, negative 3. And what just happened here, I multiplied by a negative 1. So, now what's the determinant? Well, the determinant of A is equal to minus 1 times minus 1 times minus 1 times the determinant of this, let's call this matrix B, times the determinant of B. And what is the determinant of B? Well, it's negative 24. So this will be positive 24. So that's it, right? By making use of elementary row operations, we got B into a position where it's easy to compute, or sorry, we started off with A, we arrived at this matrix B, whose determinant is very easy to compute. By keeping track of the effects, we were able to compute the determinant of A, and by computing the determinant of B. All right, that's enough for today.